Hey, good afternoon. Today we begin chapter 3, simple resistive circuits. Now, every chapter that I've covered so far, I'm sticking with the titles that are given by the book so that everything's in sync. Okay. So in the book, this resistive circuit analysis is referred to as simple resistive circuits. And so that's what I am using. All right. Simple resistive circuits. Same slide so far, but covers the most fundamental of analysis techniques in detail. So we looked at how we can connect resistors in series and parallel, right? Series and parallel. Now, we are looking at, in this chapter, we're going to look at circuits with only resistors, right? You won't even look at capacitors and inductors until you get to 211. We look at op amps later on in this chapter, which is like an off-the-shelf, 10,000 foot view. Just using it as an off-the-shelf component for circuits. But the fundamental principles that we're applying, like current in a series circuit remains the same, voltage across parallel, they all apply to all components, right? The analysis portion would be specific to resistors, but the fundamental principles apply to all components anywhere, right? So first up is a circuit that contains resistors in series. Right? We looked at resistor connections in series, resistor connection in parallel. The skill of recognizing these components, whether it's a series connection or parallel connection, that develops over time with practice. Someone catches on fast, quickly, and some others like me take a long time. Okay. So the more you practice, someday it will click. And then at that point, you'd be able to look at a circuit and immediately discern which components are in series and parallel. And depending on that, your approach will change. Okay. So resistors in series, as we stated earlier, are connected end to end, meaning they'll have a node, they'll have a junction, and at that node, at every single node, you'll have only two connections. That is the criteria. They are connected end to end. There's a node between two components. That node should not have more than two connections. Then we say those components are in series. So in this circuit right now, we have we have 8 resistors, all connected in series. Okay. Now, if you're analyzing a circuit and nothing was given to us, there's no polarity given, there is no a current direction given in the circuit, we are beginning to analyze a circuit. But the one thing we will know is we will know the source. If it's a voltage source, we would know the polarity of the voltage source. If it's a current source, we would know the direction of the current source. For a voltage source, current flows from high to low or low to high? Low to high. Current in general always goes from high to low, except when it's a source. A source is the one that's supplying energy, so it'll always flow in this direction, minus to plus. If it's a current source, the exact same thing. If you have a current source, it's going from minus to plus. Okay, that's how the polarity should be. So the point is, if we are beginning analysis on a brand new circuit, we have no idea how to begin analysis, but the first step is to assign voltage polarities to all the components and assign current directions to all the components. Those are based on assumptions, and those assumptions are based on logic and rules. And the first rule is current for a source always goes from minus to plus. So that is the point of IS. It's going in the upwards direction because the source has a plus and a minus. Does that make sense to everyone? And so once we have that, we can describe IS as going through R1, R2, R3, R4, R5, R6, R7, and back to the voltage source. Okay, it's going in a loop from the source, goes all the way around, and comes back unbroken. Because if you think about this, let's say this is a neighborhood block, 4 streets, all of them one way. If you start driving in one direction, there is no other pathway for you to take. There's only a turn. So if you have to keep moving forward, you have to make a right turn. You make a right turn, you go all the way down to the end. At the end of the block, again, there's no other pathway. There's only one street, there's a right turn. You make a right turn, you come down. Again, no other pathway except a right turn. Yeah, right. And then right turn, and you come back where you started. You form a closed loop. So in a series circuit, current always remains the same. Does not change. Well, let me rephrase that. The current is the same for all components in the series connection. Okay, so the current is the same for all components in that series connection. Same does not mean it's going to hold the same value, even if you change the component, right? The resulting current is a function of all of these resistors acting at the same time or working at the same time. Okay, if you change one of these resistors, you either remove them or you plug in 2 more in there, then the current will change, but it will still be the same for all components. Does everybody understand the distinction? In a series circuit or a series connection, the current remains the same for all components because the current is a result of all components working at the same time. Okay. So if current moves and goes through R1, R2, R3, 4, 5, 6, 7, it's entering R1 from the left, causes a voltage drop. Voltage appears across that resistor, Ohm's law. So what is the voltage polarity for R1? On the left, is it plus or is it minus? Where is the plus? Is it on the left or the right? On the left. Point of entry for a passive component. Current always goes from high to low. Temperature always goes from high to low. Pressure goes from high to low. Liquid, high to low. Current, like any other physical quantity, always goes from higher potential to lower potential, except when it's a source. Okay, law of conservation of energy applies. So current flows from high to low. So for all connections, all resistors, the voltage polarity will be in the direction of the current. Does that make sense to everyone? And this is how we determine the voltage polarities and the current direction in any given circuit. Okay, you start with the source, you look at the source polarity or the direction, and you assign the voltage polarity or the current direction, as the case may be. And from that point on, you just look and see where the current is flowing, and you apply signs and polarities. Now, even if you're incorrect in your assumption, it does not mean that your analysis will be incorrect. At the end, if you did all the steps correctly, your analysis is correct. Your answer will also be correct, except your answer will have a minus sign. That's all. Yes. So the question being asked is whether the source is supplying power or not. right? Yes, it is. So law of conservation of energy, source, as the name suggests, will supply power. It's supplying energy. Okay. And passive components are receiving energy. Okay. Passive components are receiving energy. Passive components are something that is not a source. Okay. So they are receiving the energy. A source will always supply energy, will always supply power. So in this case, Vs is supplying power. Power is associated with R1, R2, with all the resistors. Mathematically, we put a minus sign for the power supplied by a source. Otherwise, our equations would never balance out, right? We want to balance out our equations for it. So the minus sign is for us humans to work with the equations. Otherwise, our equations would never work. Real life power is never negative, but if it's a source, we put a minus sign in front of it. Okay. So let's say this is voltage Let's say this is voltage VR1, VR2, VR3, VR4, VR5, VR6, VR7. Right? If we write the equation for the voltage across each resistor, what do we get? Ohm's law. We apply Ohm's law and we get IS times R1. Make sense? Right? Ohm's law. And so similarly, we could apply Ohm's law to all of these resistors. And we can find the voltage across all of them. So far, so good, right? But the voltages are also connected in series because of the series connection of resistors. If you apply KVL around the loop, what do we get? If you apply KVL, we get minus Vs plus VR1 plus all of the voltages all the way up to VR7 is equal to 0. So the sum of all the voltages put together is equal to Vs, which makes sense. That's the only source present in the circuit. Right? 7 voltages, add them all together, should equal Vs. Yes? Right. It's from KVL. Law of conservation of energy. Everything should add up. Energy being transferred from the source, energy being absorbed across all the resistors. So what does it mean? Well, in a series circuit, current remains the same for, not remains, current is the same for all components, but the voltage is divided. Okay, voltage is divided. And this is true no matter what that component is. You can have resistors, capacitors, and inductors, all three of them in the same series connection, and the voltage would be divided. Now, the proportion of division would be different because it's not simple resistive circuit, but it would still be divided. So the fundamental principle that the current will remain the same, but the voltage gets divided applies to all components. Okay, that's one of the most important points from this topic. All right. All right, questions. Let's take a pause. Think over it. Let me know if you have any questions. So far, so good. Okay. All right, so since voltage is being divided, we can derive a technique to determine the voltage directly, and that is known as the voltage division principle. Okay, so the voltage division principle states that when you apply a voltage across a series connection of resistors, a fraction of that supply voltage appears across each resistor, and that fraction is proportional to the resistance, it's proportional to the ratio of the resistance to the total equivalent resistance in the circuit. Quite a long sentence, but mathematically it's very straightforward. Okay. Again, quite a wordy and lengthy sentence. When you apply a voltage across a series connection of resistors, a fraction of that supply voltage appears across each individual resistor. And that fraction is the ratio of that resistor to the total equivalent resistance. And that is also derived from Ohm's law. So going back to that first slide, right, we have this equation, right? From KVL, we have Vs is equal to VR1 plus VR2 and so on and so forth. Well, VR1 can all be represented Is times R1. So we get Is times R1 plus Is times R2 plus Is times R3 all the way until Is times R7. So let's do it this way. From here, actually, let me just continue down. So Vs can be Is times some R value, because the source is seeing the entire resistive network as one single resistance. A source cannot think for itself. All it knows is there is a resistor connected to it. Whether it's one resistor or is 100 resistors does not matter. Okay. So if we take this, you know what, maybe the other, let's just do it here on this side. So we had Vs is equal to VR1 plus VR2 plus all the way to VR7, right? Vs can be written as, from Ohm's law, we can write it as Is times some Req, the total resistance as seen by the source. So I can define Req as total equivalent resistance. Okay, the EQ stands for equivalent. Sometimes some authors and some professors like to use the subscript T, total resistance RT. But Req is far more common and typical. So that's what I like to use, Req. So Req is the total resistance as seen by the circuit. So I'll note that down here. Okay. These keywords as seen by, sorry, these words are very important words. As seen by means from the perspective of that component. Okay, from the perspective of that component. And I'm going to go on a little bit of a tangent and talk about this. Okay, because you will encounter this again later on in techniques in 211, 212, going forward in all classes, 306, 307, pretty much any class you take, you will need to understand this concept, right? So let's say there are 30 students in this class, right? If someone is outside the classroom and is asked the question, how many people in this classroom? They would say 31, right? But if someone asks me the same question, how many people do I see in the classroom? my answer changes to 30, not 31. So from the perspective of somebody who's outside, it's 31. The answer is different. From the perspective of somebody inside, it's 30, 30. So when you see the words as seen by, you need to find an equivalent circuit as seen by or from the perspective of a component. We must remove that component from our analysis. Okay, we must remove that component from our analysis. So if I'm making a count, I have to remove myself from that count. That's the point of that analogy. And so this circuit reduces to a source, and the source is now removed from the analysis, and you analyze the rest of the circuit without the source being present. Okay, just for theoretical analysis purposes. Okay, if you say you're looking into the circuit from the source as seen by, or it's acting as a load, that means you're removing that component from your analysis, and then you analyze the rest of the circuit between those terminals. You analyze it from between these terminals. And that's what that means. Okay. Let's take a pause and let me know if you have questions about that concept. Good. Okay. All right. So let's go back to our equation. IS times Req means the total resistance as seen by the source. And then I can write VR1 is IS times R1 plus all the way to IS times R7. You see where this is going, right? IS is common. We bring it outside. IS times Req is equal to IS times R1 plus R7. And so we have derived an equation for Req. The total resistance as seen by a source in a series connection of resistors is simply the sum of all those resistors in series. The total Req is simply the sum of the total resistors in series. And that's where the derivation comes from. Okay. So I'm assuming students are already familiar with this from physics, perhaps. Yeah. Did you all do the derivation in there? Maybe not. Okay. All right. So derivation is just for understanding, right? So where it comes from. Just a few steps anyway. Okay, so now let's go to voltage division. Voltage division, we said VR1, voltage VR1 is equal to IS times R1, right? VR1 is IS times R1. But what is IS? I can write IS in terms of VS and Req, right? We can write total voltage VS is IS times Req. Therefore, IS is VS divided by or over Req. Okay, rearranging the terms using Ohm's law. The total current IS is the total supply voltage Vs divided by the total resistance Req. And all we do is we plug in, we substitute this into each and every single equation for the resistor voltages and rearrange the terms. So once we do that, we get VR1 is equal to Vs or Req times R1. And therefore, after we rearrange the terms, I can write VR1 is a fraction of Vs, and the fraction is given by the ratio of the resistor R1 to the total equivalent resistance in that circuit. As I said, the mathematical expression is far more straightforward than the lengthy sentence. Okay. Let's take a pause and let me know if you have any questions. Any questions from anyone? Okay. So voltage division is a shortcut. Okay, it's a shortcut. It allows you to skip one or two steps. Typically, just allows you to skip one step. We must find Req. That's a given. Okay, we must find Req. Then we can directly apply this voltage division principle and determine the individual resistor voltages without needing to find or determine or calculate Is. And that's the shortcut. VR1 is Vs times R1 over Req. We do not need to find the value for Is. Remember, at the top of this course, I stated the three equations that we need for analysis are Ohm's law, KVL, and KCL. Everything else is derived from these three primary equations. So again, this is a derivation of Ohm's law or derived from Ohm's law. It's a shortcut that allows us to skip a step. We do not need to find Is. It seems very simple, but when we are working with larger circuits, it is very, very useful. Because when it's part of a larger circuit, there might be some portions of the circuit that are in parallel, some portions of the circuit that are in series, and some portions of the circuit that are neither series nor parallel. Okay, so we should be able to recognize which portion is in series, which is in parallel, and quickly apply voltage division or current division that we'll see later and determine the voltages and currents. So that's what the voltage division principle is. Okay. What resistors or which resistors are connected in series? One to the left. Any others? Any other resistors? It's 10, 40, and 20. Does anyone agree? No one else agrees? They're all by themselves? 2 people agree? How about the rest of you? I should say 5 points to them and -5 to the rest. Right? So these are said to be in series between these 2 points. That point or that node at the top and at the bottom is where you have more than 2 connections, right? So between the 10 and 40, you have this node at the top left. 40 and 20, you have this node at the bottom right, bottom left. And they do not have a third connection. So 10 is in series with 40, which is in series with 20, and that's where it ends. right? Because the 12, 20, and 180, they have more than 2 connections at their nodes. So these are in series, the rest of them aren't. So if they are in series, what is the voltage across the 12 amp source? Anyone? Well, the answer is we can't find it directly. Because if you think about it logically, current goes at the top, then where does it go? Does it go left or right? It splits in both directions. Logical conclusion is that it would split in both directions. So we don't know the value of the current that's going to the left. We don't know the value of the current that's going to the right. The first step would be to determine those values, and then we'd be able to find the voltage across that voltage, that current source. Okay. So now let's look at resistors in parallel. Resistors in parallel will share 2 nodes, the same 2 nodes. So they're connected at both ends of the terminals. And parallel connection, of course, doesn't mean that it only applies to resistors. It could apply to any and all components. Doesn't matter what those components are, right? There's only 2 nodes in the circuit, only 2. So parallel connections, no matter what components are connected, all parallel connections will only have 2 nodes. If you take any 2 nodes in a circuit, all the components connected between those 2 nodes are said to be in parallel. Okay. Take any 2 nodes in a circuit. All components connected only between those 2 nodes are said to be in parallel, which would be, in this case, 20 and 180. So you have a node at the top, you have a node at the bottom. One thing about nodes, circuit schematics, it may not always be clear on what is a node and what is not. But let's say you mark this as a node, separate node. The way to determine if it's a same node or not is to see what is connected between nodes. If there's a wire between 2 nodes, then it's the exact same node. Okay. Wire or conductor between 2 nodes means it's the exact same node. And oftentimes in a circuit, it's not always obvious. Okay, it's not always obvious. A real life example of this would be plugging a power extension cable into a power outlet. Okay. The schematic, the conductor could be very small, maybe like 1 centimeter long. It could be 1 meter long. Doesn't really matter. Everything that we see in a schematic or we do theoretical calculations is ideal. So the length of the conductor does not matter. It's the exact same node. In real life, if you take a 100-foot power extension cord and you plug it into the power outlet, what do you think is the voltage at the end of the power outlet? You would still expect to get 120 volts, right? 100 feet away. That cable may have some resistance. It's not ideal. Maybe 1 ohm or 2 ohms, but it is still the exact same node as your power outlet, even though it's 100 feet away. That's the point. Okay, so in a circuit schematic, it may not always be obvious what is a node and what is connected in parallel. But if you just mark out all the nodes in there, and if you see a wire or conductor between the two nodes, then it's the exact same node, right? So here, 20 is in parallel with 180. This is my symbol for parallel. Two slanting horizontal lines, parallel. Anyway, so that's parallel. Let's see how we can reduce them. So connected at both ends, and because it's the exact same node, the voltage between those two nodes will be exactly the same for all components. In series connection, the current is the same for all nodes, for all components. But in a parallel connection, the voltage is the same for all components because the voltage that appears between those two nodes is a result of all components working together. If you change out any one of those components, the voltage will change, but it'll be the same for all components. This again is a fundamental principle that you should remember. Okay, if you have a parallel connection, then the voltage for all components connected in the parallel connection is exactly the same.
Is there an adapter here? I think I left it. No?
So if there are two nodes and you take out, let's say, R2 from this connection, voltage would change because now you have R1, R3, and R4 in there, but that voltage will remain the same for all three of them. Makes sense to everyone? But let's look at what happens to the current. For explanation purposes, it's easier to deal with current sources. So we just drew a current source in there. But again, current source and voltage source exactly the same. It's just the mode of operation. So current IS comes here, goes around. What happens to IS when it hits node A? Or point A, not node A, point A. It splits, right? So it splits. Some of it goes down R1, some of it goes down B. When it hits point B, some of it's going to go here. Some of it's going to go there. It's going to keep on splitting. Then makes a right turn, goes through R4. That current comes through here. IR3 comes down, merges with IR4. Let's call this IS, IR1, IR2, IR3, and IR4. Okay. And then IR2 comes down, merges with this. IR1 comes down, merges with this. And then it combines to form IS again. Okay. That's the logical order of steps that you should take when you're working with an unknown circuit. Okay, you're applying current directions. You start with the source, and from the source you can assign current directions and voltage polarities. Because the currents are coming from the top and going down, all of them have voltage polarities plus at the top and minus at the bottom. Even without looking at the current directions for resistors, we know that the current source is going in the upwards direction. That means current source polarity is minus at the bottom and plus at the top. And because the nodes are exactly the same, all resistors will also have the same polarity. Okay. All right, let's look at the derivation. Actually, for the next one. Let's see, voltage division, did I cover? Yeah, I think everything is covered here. Okay. All right, so voltage remains the same. The current splits, so the current is being divided. So in a parallel connection, the voltage remains the same for all components, but the current gets divided. Hence, voltage is same for all components, and the current is divided across, or not across, between. Voltage is always measured across, current always flows through. Okay, keep that in mind. When you choose your words, voltage is always across, current is always through. So voltage is divided across series connections, current is divided between parallel connections of resistors. Okay, so I can apply KCL at the top, and I can get IS is equal to IR1 plus IR2 plus IR3 plus IR4, right? And then voltage VS is the same as V1. Oh, V1, same as V2, same as V3, same as V4. The voltage remains same, current is divided. And from Ohm's law again, I can state that the current source is seeing all the resistors as one single total equivalent resistance, and I can draw the circuit as seen by, or from the perspective of, current source IS. REQ, and this is IS, right? And of course, the voltage across here is VS. So from Ohm's law, I can write total voltage VS is equal to IS times REQ, right? I can write IS is VS over REQ. VS is equal to IS is equal to IR1 plus IR2 plus IR3 plus IR4. And I can write IR1 would be VR1. I know the diagram from the book uses V1, but I like to refer and be specific VR1. That relieves or removes all ambiguity. VR1 is the voltage across resistor R1. So VR1 over R1 plus VR2 over R2 plus VR3 over R3 plus VR4 over R4. But VR1 is the same as VS. VR2 is the same as VS. VR3 and VR4 are also same as VS. So everything can be replaced with VS because they're the exact same voltage. We take it out and we get 1 over REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. Final step, which I'm assuming all of you are familiar with, the equation for REQ. REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. And the reciprocal or the inverse of that sum. Okay. 1 over R1 plus R2 plus R3 plus R4. Equation is familiar, right? Derivation? Not done before. Okay. That's where it comes from. So that's REQ. Now, if I wish to find each individual current, all I need to do is apply Ohm's law again. I apply Ohm's law. I need to find the current in each individual resistor. I can write IR1 is Vs over R1. It's the same voltage, Vs. And Vs is equal to Is times Req. So that's 1 over R1. I rearrange the terms, and I can get IR1 in terms of Is. So parallel connection, each individual current is a fraction of the total supply current, and the fraction is given by the ratio of Req to that resistor. Req over R1. Okay, Req over R1. And that is the current division principle. It's exactly the same as the voltage division principle, except the ratio numerator and denominator are flipped or switched. Did y'all study current division and voltage division in physics? Some of them says yes, some of you all say no. Okay. Couple of minutes left. I want to bring up a few key points about resistors in parallel. When you have resistors in series, you simply add them up. The human brain automatically knows if you add something to something, number would be larger, especially positive numbers added together would be larger. So Req in a series connection is always larger than any resistor in that series. In a parallel connection, the Req is always smaller than the smallest resistor in that parallel connection. Okay, Req is always smaller than the smallest resistor in the parallel connection. So if you have a let's see. Okay, right here. So we have a parallel connection of 20 and 180. So the Req of these two together will be less than 180. Oh. Req. I need some coffee. Req would be less than 20. That 20 is the smallest resistor in the parallel connection. So Req would be less than 20. If your answer is not less than 20, that means there's an error somewhere in your calculation. So that's a quick verification step. And the reason I emphasize this is because I've had students who are in their third year, fourth year, they are in a rush to solve, not enough time to solve, so in a rush. But somewhere along the way, they make a small error and they neglect to verify this. It's a parallel connection. Your Req must be smaller than the smallest resistor. It's a quick verification. You don't need to perform any calculation. One other thing about parallel connection, if So it's close to 4. If you need to leave, you can leave. But if you have n number of resistors connected in parallel, all with the same value, all with the same value R, then what is Req? Anyone know this? Req is R divided by N. If you have two resistors in parallel, same value, 20 ohms in parallel with 20 ohms, Req is 10. If you have three resistors in parallel, 30, 30, 30, Req is 10. Okay. Announcement about the Friday quiz was posted on Canvas. Monday quiz will be as usual. Friday quizzes, if you have not yet read, I'm not implementing it for now. So I'm merging that category with the Monday quizzes. And if you do have one Friday quiz later on in the quarter, one or two perhaps, then it will be part of the overall quiz section. Yeah, and that's it. We'll end class here today, and I will see you all on Monday.